You feel it right now, the weight of your own body, the pull of the earth. But what if I told you that everything you've ever been taught about gravity is wrong? That what you're actually feeling is a cosmic illusion, a lie told by your own senses? The truth, proven by satellites, black holes, and the very GPS in your phone, is so much stranger. Gravity isn't a force at all. It doesn't pull you down. So what is it really doing? And why does this change everything? There's something profoundly unsettling about the simplest things, like the feeling of standing up, the sensation of your own weight, the absolute certainty that if you let go of something, it will fall. This isn't just knowledge. It's a core part of our physical reality. It feels like a fundamental truth written into the fabric of the universe. We call it gravity, and we've been taught for hundreds of years that it's a force, an invisible hand pulling everything downward. But here's a fact so bizarre, so counterintuitive, that even saying it out loud feels strange. Gravity is not a force. What you feel when you stand on the ground, that pull, that pressure in your feet, is a complete illusion. A misunderstanding baked so deep into our biology and our history that it took a genius to unravel it. What I'm about to tell you isn't a fringe theory. It's not a what if. It is the bedrock of modern physics, confirmed by countless experiments and observations, from the ticking of GPS satellites to the ripples in space from colliding black holes a billion light years away. Our universe does not work the way it feels like it works. The story of gravity is the story of how wrong our instincts can be and how beautiful the truth turns out to be. This is the story of how we discovered that gravity isn't a pull from the earth, but a curve in the shape of reality itself. Let's start with what we think we know. For most of human history, gravity was just heaviness. Things fell because they wanted to reach their natural place. Earth fell to earth. Fire rose to the heavens. It was intuitive, based purely on observation. Then came Isaac Newton. The legend says an apple fell. The reality was a mind that saw a deeper pattern. In the late 1600s, Newton proposed something revolutionary: universal gravitation. His idea was elegant and powerful. Every single piece of matter in the universe, from an apple to a planet, attracts every other piece of matter with a force. The strength of that force depends on two things: the masses of the objects and the distance between them. Double the mass, double the force. Double the distance, the force becomes 4 times weaker. He captured this in a neat, compact equation: F equals G asterisk M1 asterisk M2 slash R squared. This was a monumental achievement. For the first time, the same rule explained why an apple falls and why the moon orbits the earth. It unified the heavens and the earth. It was predictive. Using this law, we could calculate planetary orbits with stunning accuracy. It led to the discovery of Neptune simply by looking at the wobbles in Uranus's orbit. Newton's gravity sent us to the moon. It works spectacularly well. But there was a problem, a deep philosophical itch that Newton himself couldn't scratch. The problem of action at a distance. How exactly does the sun, 93 million miles away, reach across utterly empty space and pull on the earth? How does the earth, right through the vacuum under your feet, exert a force on you? In every other part of physics, forces need a medium, a mechanism, contact. You push a book with your hand. Sound travels through vibrating air. But gravity? It seemed to work through nothingness instantly. This deeply troubled Newton. He famously wrote, "I frame no hypotheses regarding how this could be." In other words, I don't know how it works, but the math describes what we see perfectly. This was the first crack. Gravity as a mysterious, instantaneous pull was elegant, but it felt like a description, not an explanation. The cracks kept growing. In the 1800s, astronomers noticed a tiny, persistent glitch in the solar system. The planet Mercury, the closest to the sun, has an elliptical orbit, but that ellipse itself was slowly rotating or precessing around the sun. Newton's gravity could explain most of this precession, but not all of it. There was an unaccounted for 43 arcseconds of rotation per century. It was a tiny discrepancy, a single degree every 10,000 years, but it was real, measurable, and stubborn. Astronomers scrambled, proposing an unseen planet called Vulcan near the Sun. But Vulcan was never found. The math of Newtonian gravity was off, if only by the tiniest fraction. Then, in 1905, Albert Einstein shattered our concepts of space and time themselves with his special theory of relativity. He showed that space and time are not separate, absolute stages, but are woven together into a single fabric, spacetime. He also showed that nothing, no information, no influence, can travel faster than the speed of light. This created a direct collision with Newton's gravity. If the sun suddenly vanished, Newton's law implied the Earth would instantly fly off in a straight line. But according to relativity, the Earth wouldn't know the sun was gone for about 8 minutes, the time it takes light to travel from the sun to Earth. So, when would the gravitational pull disappear? Instantly? Or after 8 minutes? Newton's idea of an instantaneous force was now incompatible with the cosmic speed limit. Einstein saw these problems not as minor bugs, but as symptoms of a fundamental flaw. He spent the next decade on an obsessive quest to rebuild gravity from the ground up. He started with a simple, almost whimsical thought experiment that would become the seed of a revolution: the equivalence principle. Imagine you're in a small, windowless room. You feel your feet firmly on the floor. You drop a pen. It accelerates to the floor. You weigh a certain amount. Are you standing still on the surface of the Earth, feeling its gravity? Or are you in a spaceship, out in deep space, being accelerated by a rocket engine at 9.8 meters per second squared? Einstein's brilliant realization was, there's no experiment you can do inside that room to tell the difference. The effects of being in a gravitational field and the effects of being in an accelerating reference frame are perfectly, exactly equivalent. The force you feel on your feet, the way dropped objects behave, it's all identical. This seems like a curiosity, but it's a philosophical earthquake. It links gravity and acceleration. It suggests that the force you feel might not be a fundamental force at all, but something that arises from your state of motion. From this seed grew the general theory of relativity, published by Einstein in 1915. Its core idea is as radical today as it was then. Gravity is not a force. It is the curvature of spacetime. Let's break that down, because it requires a complete shift in perspective. First, accept Einstein's concept from special relativity. Space and time are a unified, four-dimensional continuum called spacetime. Every event, like the pen hit the floor at 3 p.m., is a point in this four-dimensional fabric. Now, in special relativity, this spacetime is flat. It has the simple, predictable geometry we're used to. In flat spacetime, objects with no forces acting on the move in straight lines at constant speeds. Einstein's leap was this. What if the presence of mass and energy doesn't create a force, but instead warps or curves this fabric of spacetime itself? A massive object like the sun isn't pulling on things. It's creating a depression in the cosmic fabric, like a bowling ball placed on a stretched rubber sheet. Here's the crucial part. In this curved spacetime, the straight lines are no longer straight in the classic sense. They're the shortest paths between points in a curved landscape. These paths are called geodesics. And here is the complete inversion of Newton. An object under the influence of gravity alone, like Earth orbiting the sun or a pen falling, is not being acted upon by a force. It is simply following a geodesic, the straightest possible path, through a curved spacetime. It is moving inertially, freely, with no forces at all. Think about the Earth orbiting the sun. Newton says, the sun's gravitational force pulls the Earth inward, constantly bending its path into a circle. Without this force, the Earth would fly off in a straight line. Einstein says, the sun's mass curves the spacetime around it. The Earth is simply following a straight-line geodesic in that curved geometry. From the Earth's perspective, it's coasting freely. It's just that in the curved geometry near the sun, a straight line happens to be a closed elliptical orbit. There is no pull. There is only geometry. This explains the equivalence principle perfectly. When you stand on Earth, you're trying to follow a straight line geodesic towards the Earth's center. That's freefall. But the solid ground is in your way, pushing up on you, constantly accelerating you upward. What you feel as weight is not the pull of gravity. It is the upward push of the ground, preventing you from following your natural, force-free geodesic path. In the accelerating spaceship, you feel the same push from the floor of the ship. In both cases, you're not in free fall, but being accelerated, and that feels like a force. This geometric view of gravity makes stunning, testable predictions that Newton's force-based view could not. Almost immediately, it solved the Mercury problem. The precession of Mercury's orbit wasn't due to a missing planet. It was because Mercury, being so close to the Sun, was moving through the most curved region of the Sun's spacetime. When Einstein calculated Mercury's orbit using his new field equations, the extra 43 arcseconds per century appeared exactly, with no fudging. It was the first major victory for general relativity. Then came the 1919 solar eclipse expedition led by Arthur Eddington. Einstein predicted that starlight passing very close to the Sun would not travel in a straight line, because there are no straight lines in curved spacetime. The light would follow a geodesic, which would be bent by the Sun's mass. This meant stars appearing near the Sun during an eclipse would be shifted slightly from their normal positions. Eddington's measurements confirmed the prediction. Light, which has no mass, was bent by gravity, something nonsensical in Newton's theory where gravity pulls on mass, but perfectly natural if gravity is the shape of space through which light travels. Overnight, Einstein became a global icon. The predictions grew stranger and more profound. General relativity said that time itself is affected by gravity. In a strong gravitational field, near a massive object, time runs slower relative to a weaker field. This isn't a mechanical effect. It's because time is part of the curved space-time fabric. This gravitational time dilation has been confirmed with extraordinary precision. Atomic clocks on GPS satellites, which orbit high above Earth where gravity is slightly weaker, run faster than identical clocks on the ground. If this effect weren't corrected for, GPS would be useless, accumulating errors of miles per day. Your phone's navigation is a daily, practical proof that gravity curves time. The theory also predicted extreme objects. If enough mass is compressed into a small enough volume, it could curve spacetime so severely that nothing, not even light, could escape from a certain boundary. John Wheeler would later name these objects black holes. For decades, they were a mathematical curiosity. Today, we have direct evidence of them. We've heard the space-time ripples from their collisions with LIGO, and we've taken a picture of the glowing gas swirling around the supermassive black hole in the galaxy M87, its shadow perfectly matching Einstein's predictions. And those ripples, gravitational waves, are perhaps the purest expression of gravity as geometry. If two black holes orbit each other, their violent motion doesn't create a waving force field. It literally sends ripples in the very curvature of space-time itself out across the universe, like waves on a pond. When these waves pass through Earth, they very slightly stretch and squeeze space itself. In 2015, LIGO detected this stretching, a change in distance 1,000 times smaller than an atomic nucleus, caused by two black holes merging over 1 billion years ago. We didn't detect a force. We detected the fabric of reality ringing like a bell. So, if this geometric picture is so successful, what about the familiar force of gravity we calculate with F equals gm1m2/r²? It's an approximation. In our relatively weak earthly gravitational field, and at speeds much slower than light, the curvature of space-time is minimal. In that nearly flat geometry, following a geodesic looks, for all practical purposes, exactly like being pulled by a force. Newton's equations are an excellent, simplified user manual for the solar system and our daily lives. But they're a simplification of a deeper geometric truth. This leads us to the frontier and to the greatest unresolved tension in modern physics. We have two incredibly successful theories. General relativity, which describes gravity as the smooth curvature of space-time on large scales, and quantum mechanics, which describes the other three forces, electromagnetism, the strong and weak nuclear forces, as exchanges of force-carrying particles, like photons, on tiny scales. These two theories are fundamentally incompatible. When we try to describe gravity in the quantum language of particles, we mathematically predict a particle called a graviton, a massless particle that would mediate gravitational interactions. But the math breaks down, producing infinities we can't resolve. Conversely, the smooth, deterministic spacetime of general relativity falls apart in the chaotic, probabilistic quantum world of the extremely small, like at the center of a black hole. This conflict suggests that our understanding, even with relativity, is incomplete. At the most fundamental level, perhaps spacetime itself is not smooth, but quantized, made of tiny, discrete grains. Perhaps it is emergent from something even deeper. Theories like string theory and loop quantum gravity are attempts to bridge this gap, to find a theory of quantum gravity. But make no mistake, the quest for quantum gravity does not demote Einstein's revelation. It seeks to understand the nature of the stage itself, the spacetime whose curvature is gravity. Whether spacetime is fundamental or emergent, the description of gravity as curvature, not force, remains the accurate map for the universe at every scale we have been able to test, from the fall of an apple to the evolution of the cosmos. And what a cosmos it is! General relativity doesn't just describe attractions, it describes the universe itself. The equations allow for solutions where the entire fabric of spacetime can expand or contract. In the 1920s, Edwin Hubble discovered galaxies are all moving away from us, implying the universe is expanding. The logical conclusion, running the clock backward, is the Big Bang, not an explosion in space, but the beginning of spacetime itself. The expansion of a universe isn't galaxies flying apart through static space. It is space itself stretching, carrying galaxies along. This is only conceivable if spacetime is a dynamic, malleable entity. Today, we measure that this expansion is accelerating, driven by something we call dark energy. In Einstein's geometry, this can be described as a property of space itself, a constant background curvature that pushes things apart. The fate of the universe is written not in forces, but in the geometry of the cosmic fabric. So, let's return to where we began. You, standing on the ground, feeling your weight. In the Newtonian universe, you're at rest. The ground is solid and still. A mysterious force from the earth pulls your body down, and the ground resists, creating the sensation of compression. In Einstein's universe, the truth is inverted. The Earth's mass has curved the space-time around it. Your natural unforced state of motion is to follow a geodesic, to fall freely along that curve toward the center. You are not at rest. You are constantly trying to fall. The ground is not passive. It is violently accelerating upward, pushing against your feet to stop you from following that natural path. You're being pushed up, not pulled down. The force you feel is the contact force from the ground, not gravity. Gravity, in its pure form, is what you feel in the brief moment of freefall, which is the sensation of no force at all. This is the profound correction. Gravity is not something that happens to objects within space and time. It is the shape of space and time. Matter and energy tell space-time how to curve. Curved space-time tells matter and energy how to move. The universe is not a static stage with actors being pushed and pulled by invisible strings. It is a dynamic, malleable, geometric entity where the stage itself is the primary actor, its curves and contours dictating the motion of everything upon it. The falling apple, the orbiting moon, the bending starlight, the slowing of time, the collision of black holes, and the expansion of the entire cosmos, all are simply expressions of things moving freely along the straightest possible paths in a curved and rippling reality. So the next time you feel your weight, remember, you are not being held down. You're being held up. And the true nature of gravity is not a pull into the earth, but a curve in the path to the stars.